This is the differential equations packet, page 2. We're talking about solving a differential equation by graphing using something called a slope field. We'll talk about this in just a minute, but there are going to be times where finding the answer to a differential equation is going to be extremely difficult, possibly even impossible. And so is there something else that we can do to help us find some information about the solution? And the answer is yes, so using something called a slope field. So let's start with an example. Example 4, find the general solution to the differential equation dy dx equals cosine x. So we'll start by anti-deriving both sides, and I get y is equal to the sine of x plus c. So this is a pretty straightforward solution, nice and easy. We have the general equation, sine of x plus c. We know that c could stand for any constant. So let's take a look, though. Consider solving the same differential equation by graphing. To do this, what we're going to do is we're going to generate something called a slope field. That is, I'm going to take a particular point, such as the point 1, 1, and I'm going to plug 1, 1 into my differential equation. So I'm going to plug 1 in for x, plug 1 in for y, and then I'm going to solve that equation for dy dx, because dy dx would be the slope of the equation at that point 1, 1. And so what I'll be able to do is draw just a little segment that has a slope of 1. And that should give me a glimpse. If I do that enough times with enough points, that should give me a glimpse of what the general solution for this differential equation looks like. So to do that, what we're going to do is we're going to go ahead and create a little column for x, create a column for y, and create a column for dy dx, which is just the cosine of x. Now, I want you to notice in this example that there is no y in my dy dx. That is, my slope depends entirely and only on what x is. So let's just take, for example, a point. Let's just take the point 0, 0. So at 0, 0, the slope is going to be whatever the cosine of 0 is, which is 1. So at 0, 0, I am going to draw just a little line segment with a slope of 1. Now, if I go, what about the point 0, 1? Well, because dy dx depends entirely on x and only on x, then the dy dx would also be 1 there. So at the point 0, 1, we have another line segment. And that would hold true for every point that has an x-coordinate of 0. And that would be everything on the y-axis. Well, let's move on. Now, what does this represent? Well, because it's unscaled, we can choose what we want to represent. Sometimes it'll be 1, 2, 3, 4. Because trig functions really work well with values of pi over 2, we're going to go ahead and let our scale be pi over 2 for this. That would be pi. This would be 3 pi over 2. This value is 2 pi, and we'll stop there. We'll also go back a little bit and work on that. So let's move on to pi over 2. Well, again, it doesn't matter what this y-coordinate is. I'm going to take a look at this point right here on the x-axis. The cosine of pi over 2 is 0. So that means at this point, I draw a little line segment that has a slope of 0. And for that matter, every point that has a x-coordinate of pi over 2 is going to have a slope of 0. So just little line segments, slope 0. Let's move on to pi. Again, y is 0. We'll start with that. Cosine of pi is -1. So again, I'm going to go -1 here. And every point move on to 3 pi over 2, which also has a cosine of 0. So we're back to 0 here. And then to speed things up, at 2 pi, we're back to a slope of 1. Now, I'm not going to take the time to write this. I'll let you verify this on your own. But when x is negative pi over 2, we're going to have a slope of 0. At negative pi, we have a slope of -1. -3 pi over 2, we're back to 0. And at negative 2 pi, we're back to positive 1. So I know that was a little rushed, but if you have questions, definitely just go ahead and email me and we can go through this. Now, watch this. Compare this slope field with the multitude of graphs from example 4. So what I want to do is I want to jump to our TI calculator. And what I've done here is, going back to the y equals, I have plotted sine of x, and I gave us a few constants, 1, 2, 3, and then negative 1, negative 2, and negative 3. And so we get all these graphs are the solutions, the general solutions, to the differential equation dy dx equals the cosine of x. So I want you to compare what's on the screen right now with your slope field. So compare this right here with this right here. And what I want to do is take my pencil and just kind of sketch. So if I follow this, if I draw a curve that has a slope of 1 here, we go up, then at this point, by the time I get up to this point, my graph has to level out, has to be 0. And then by the time I get to this point over here, we're going down at a slope of negative 1. And by the time I get to here, we're at 0. Back up to here, we're back to positive 1. Continuing down and up, back down. So if I were to do this over and over and over again, what you would see is I'm doing nothing more than tracing out exactly what was just on the screen of the calculator, which is the graph of the sine of x plus any number of constants. So the slope field gives us a glimpse of what the solution to the, or the general solution to the differential equation is. So let's just go over these 4 key points and then look at that 5th question about dealing with slope fields. So key point number 1, a function's slope field can be quickly created from the differential equation. And it's quickly because primarily it's just calculations. It can be some tedious sometimes as we're doing quite a few calculations. But still, it can be quickly created without a whole lot of effort. The slope field represents the general solution to the differential equation. To complete the slope field, you plug in any coordinate pair into the differential equation, draw a short line segment at this coordinate with a slope equal to your answer from this first part here. Now, what we'll get into in the next page is, what if we have a particular solution? So in other words, what if I wanted to draw the particular solution that goes through this point? Well, then what we would have is we would have the single solution that travels through this point. So we're able to then sketch out at least what the particular solution is going to look like. And so I think we've pretty much answered this, but why is the slope field useful when solving differential equations? Again, partly because we are given some differential equations that are either difficult, if not impossible to solve, and the slope field gives us a glimpse at what the general solution for the differential equation will look like. Okay, we'll go on to page 3 in the next video.